Professor Inhi, for the kind introduction, and thank you very much for providing me this good opportunity to talk in front of a so big audience. And so today, my name is Takahiro Tsubota from Ehime University, and so I have two lectures. So one is about traffic state estimation, and the other is traffic accident risk estimation prediction model based on the deep learning. The first lecture is more like the basic lecture about the traffic engineering and containing some of my research outputs. And so let me start with this traffic state estimation lecture. And before starting my lecture, I will just quickly show you where I am from. So this is Japan, and university and city of Matsuyama is located in here, and in this small island. And there are, in this small island, and Matsuyama is around here. And we have the direct flight to Osaka and Tokyo, and it takes about 90 minutes or 60 minutes. So it is a bit countryside, but very convenient location. And if you come to this city, we have, so this city of Matsuyama and Ehime Prefecture is very famous for the cyclists. We have this big bridge from here to all the way to Hiroshima. There are many islands and there are many bridges between the islands, and cyclists can travel from Ehime to all the way to Hiroshima using these beautiful bridges. And also, this city of Matsuyama is famous for the hot spring called Dogo Hot Spring. So if you have a chance, please come to Matsuyama. It's a very good place for the sightseeing. And let me start the lecture today. And I will start from very basic concept about the traffic engineering and traffic monitoring. So what is why we have to mitigate the traffic congestion? So this question is quite obvious, but let me start from this one. So traffic congestion affects in many sides, in many aspects, like due to the traffic congestion, we have to experience extra time, and also we have to consume extra fuels. So it has a big economic loss. And also due to the traffic congestion, we cannot predict the travel time. So so normally it takes 10 minutes, but sometimes it takes 15 minutes, or sometimes it can be 20 minutes, but we don't know. So it causes the travel time unreliability. And also it causes the high emission and energy use. So it has the environmental impact. And also there are many bad effect on the job and services. So obviously the traffic congestion has to be mitigated. And the cause of traffic congestion is very easy. So let's see the diagram on the right-hand side, and the x-axis is the time, and y is the traffic demand. So the demand is small during the night, but it gradually increases and go to the peak. And so that's the demand. And after the peak, the demand decreases gradually. That's the demand side. On the other hand, the road has the capacity. Capacity is normally like this, the constant. And if the demand exceeds the capacity, the congestion starts. And if the demand goes below the capacity, then the congestion gradually decreases. So that's a very basic idea of the congestion. So the congestion begins when the demand temporarily exceeds the capacity. And the congestion starts at this point. So when the demand exceeds the capacity, the congestion starts. So the diagram on the bottom is a concept as an illustration of the queue length. Y-axis is the queue length. And when the demand exceeds the capacity, the queue starts grow up, and it becomes the maximum queue length at this point. So at this point, the demand goes below the capacity. But at this time, the queue is still at the maximum. And when this queue disappears, it disappears until it disappears all the way after the demand below the capacity. So the traffic congestion, the impact once the congestion happens, the impact continues very long time. And also during that time, the queue during that time, the Q propagates to the upstream, and eventually the effect goes to the network-wide. And in the worst case, the network becomes gridlock state where no vehicle can move. The congestion is so severe that the vehicle cannot move anymore. So that's a gridlock. So the congestion has impact on the network-wide. And to mitigate the congestion, there are basic three approaches. One is, so this is the capacity level, and one approach is to increase the capacity. If we increase the load capacity, then the impact of the congestion significantly decreases. So, and the main approach is the signal optimization or geometric improvement, like increasing the number of lanes, or quick response to the traffic accident. So by doing these approaches, we can increase the capacity and decrease the congestion. And the second main approach is to reduce the demand. So by distributing the demand spatially. So if all the people use one road, the demand significantly exceeds the capacity. But if they can distribute spatially, then the demand on this road can be decreased to this level so that the congestion becomes smaller. So this is the second strategy. The third strategy is to distribute the demand temporarily. So the congestion occurs because all the people want to use the road at this time, but if some of them depart earlier, or the other people may depart late after the busiest time, then the peak of the demand can be smaller and the congestion can be mitigated. So this is another third approach is to distribute the demand over time. But in any strategies, we have to know, so all these strategies require the timely and reliable information about the current traffic state, because if we know the demand and the capacity, we can easily implement such a strategies. But normally, we don't know the demand and capacity. Conceptually, we can draw this kind of diagram, but normally we don't know the information of the demand and capacity. So instead, we have to monitor the network and identify. So this is a desirable condition where the demand is smaller than the capacity. And this is an undesirable condition where the demand exceeds the capacity. And we have to monitor and keep the state in the desirable condition. So that's the key idea of the traffic control. And yeah, to do that, we need to properly and accurately understand the link and network performance through the network monitoring. But yeah, as I mentioned, we normally don't know the shape of the demand curve and the exact number of the capacity. So in that case, what we can monitor? So that's the question for the traffic monitoring. And we all know so we have three key variables to monitor the traffic, to describe the traffic states. So the one is the flow, and the second one is the density, and the third one is the speed. The flow is the number of vehicles passing in a unit time. So that's the flow. So it's not just the number of vehicles. The flow is the number of vehicles passing the section in a unit time. So that is the idea of the flow. On the other hand, the density is the number of vehicles occupying the road section. So this is the number of vehicles. They don't have to move. If there are many vehicles, then the density is high. So that's the difference of the flow and density. And the third variable is the speed. So that's average moving speed in a section. So that's the speed. So we have three key variables to describe the traffic state: flow, density, and speed. And also, I think you all know about this, and we have this fundamental equation between these three variables. These three variables are not independent variables each other. Instead, they follow this equation, Q equal K times V. So yeah, these variables are not independent, and the meaningful traffic states should be described by considering their relationship. If we look at each variable independently, we can't get much information. But if we see these variables with the combination of, for example, flow and density, we can get the meaningful information about the traffic states. And I will show you why one variable is not enough. And for example, flow. If we only have the information about the flow alone, then this variable of flow has a problem, because the flow, the same flow can be observed in free flow state and the congestion state. For example, if the flow is small, we normally think if the value of the flow is small, we assume that the network is in a free flow state where smaller amount of vehicles are driving. So this is a very general, very natural idea. But the small value of the flow can also be observed in a congestion state, because during the heavy congestion, vehicle cannot move. Vehicle moves only small speed. So please remind the definition of the flow. The definition of the flow is the number of vehicles passing the section. So even if there are many vehicles on the road section, if they are moving very slowly, then the number of passing vehicles in a section is quite small. So the same flow can be observed in free flow and in congestion. So the variable of flow itself doesn't tell much information, actually. And speed also. Speed without volume doesn't have much information. Please remind the Google Map traffic information. I think many of you use the Google Map traffic information, and some road section can be red, and the red indicates the link is heavily congested. But we don't know the number of vehicles actually in the link from Google Map information, because it only tells the speed of the vehicle. So there are two cases. One case is the road link is actually heavily congested, so the speed is quite low, and Google Map shows in red. So this is one case. But on the other hand, another case can be considered, like there are very small number of vehicles are driving, but they are just driving very slowly. For example, if small number of vehicles are just driving to look for the parking area, they drive slowly, and their movement can be shown in a Google Map. So this is not just congestion. Small number of vehicles are just moving slowly. This is not actual congestion. So speed alone, the variable of speed alone doesn't tell much information as well. And the travel time also insufficient to describe the traffic state. So for example, we can draw this kind of graph using the travel time information. So y-axis is the travel time, and in the early morning it is free flow, so the travel time is small. But when the peak time, we observe longer travel time. And in the off-peak time, the travel time becomes small again. And in the evening peak, again, we have longer travel time. This travel time information is very useful for us to plan our trip. But this is only, so these parts just tells us we observe the longer travel time. But we don't actually know how much the road is congested in this time, or how desirable or how undesirable condition. We don't know such information from this travel time information. Then what we need to describe the traffic state is the relationship between at least two variables. And the most important relationship is the QK relationship. Q is the flow and K is the density. So this is a typical QK relationship, QK fundamental diagram. X-axis is the density and Y-axis is the flow. And once we can get this kind of QK diagram, then So when the density is small, where the number of vehicles are small, then the flow increases as the density increases. But if there are too many vehicles on the road, then the flow decreases with the density increase. And when the density is at this level, we can observe the maximum flow. So this is a kind of control target, operational target. And the left-hand side of this operation target is called free flow state. And the state on the right-hand side of the operational target is called congestion state. So this QK relationship tells us what the traffic state is. So we need at least two variables, and the density and the relationship of the density and the flow is very important. Now, I will move on to how we can monitor the traffic state by using this time-space diagram. I'm not sure if you are familiar with this time-space diagram, but let's say, so x-axis is the time, and y-axis is the space, I mean the road section, and the vehicle is moving from bottom to up, and each line represents the vehicle movement. And the slope is the vehicle speed. And this part, you can see the steeper slope, and this part, you can see the flatter slope. And so this steeper slope represents the vehicle are driving in a free flow speed, whereas this flatter trajectory represents vehicles are driving in a slower speed. So that means this part is the congestion state, and this part is the free flow state. And if we can get this trajectory diagram for all the vehicles, we can get the perfect information about the traffic state. For example, so on the right-hand side, I kite the vehicle trajectory diagram using the vehicle speed. So if we color using the speed information, we can clearly see, okay, this part is a free flow state, and this part is a congestion state. And there is something, in this part, the bottleneck is here. So at this is the start of the congestion, and the congestion propagates up to this part. And yeah, from this trajectory information, we can get the full picture of the traffic state. And not only speed, but also the number of the trajectory represents the flow, and also flow, and the number of the trajectory represents the flow, and also the density as well. So we can get the full information, full traffic state information from this trajectory information. So that's the ideal case. But in reality, we only have some sensors to monitor the traffic states. And the most major sensor is the roadside detector. So let's say we have detector at here and here. And what detector? So the right-hand side is full information, full trajectory information. On the other hand, I will show what these detectors see this traffic state. So it is like this. The detector can only observe the traffic state where the detector is installed. So it's like this. And in these days, we have probe vehicle data, but unfortunately, probe vehicle equipment is not for every vehicle. So it's just a partial observation. So even if we have probe vehicles, it's like this. We know the trajectory of some vehicles with GPS equipment, but it's just a partial observation. So this is what we can see from the sensor. On the other hand, the right-hand side is full trajectory. Okay. So yeah, vehicle detector only see the traffic state where the detector is installed. So we can only know, for example, traffic volume or time occupancy at these points. And the probe vehicle we can observe full trajectory for this road section, but unfortunately, the sample rate is not very high. So we can know the information about speed and travel time from these probe vehicle data. But from this data, we cannot observe the traffic volume or traffic density. So traffic flow can be observed using detector, and the travel speed can also be observed by the probe vehicle data, but the direct measurement of the density is very challenging. So that's why we need the traffic state estimation techniques. Yeah, so this is a quick summary up to here. So fixed detector observe the point measurement, and the probe vehicle observe full trajectory, but it's just a sample data. The sample size is quite small. But on the other hand, the traffic is strongly affected by many factors like signals or queue and side street effects. So how can we observe the traffic states? And this diagram shows the difference of signalized arterials and motorway sections. Motorway section is quite simple because there's nothing in a motorway. So vehicle can continuously move. They don't have to stop, basically. They can just keep driving along the road. And also, there's a limited access. We can only access to the motorway by on-ramp and off-ramp. And yeah, so there are only limited access. And also, the traffic condition is relatively homogeneous. And the queue only happens at some bottlenecks. So traffic state estimation for the motorway is not really challenging. But for signalized arterials, the situation is totally different because the movement of the vehicle can be interrupted by many factors like, yes, of course, we have traffic signals. And we have to stop at there. And not only that, but also we have like parking, on-road parking that interrupt our drive. And also there are cyclists or pedestrians. So there are many factors that interrupt our driving in the signalized arterials. And also there are many access. So if there is side street, some vehicle can come here, or if there is a shopping center here, some vehicle want to enter this shopping center, and that vehicle will block the following vehicle, and another congestion happens. So there are many factors in the signalized arterials. So traffic state estimation of urban street is quite challenging. So, and also even when we have the detector, so the detector information is not very useful, cannot be very useful because detector information can change depending on their location. In some cases, traffic detector is located in, we have the signalized arterial and the traffic signal is there. And for this situation, we can expect this kind of trajectory. And yeah, during the green time, the vehicle can move without stopping. But if the signal becomes red, they have to stop in front of the signal. So we can expect this kind of trajectory diagram. And if we have the detector in a mid-section or upstream section, then this detector observes this traffic state. So at this point, most of the vehicles are just moving. So this detector is mainly observing the moving vehicle. So the density estimated from this detector can be underestimated. On the other hand, in Japan, we mainly have the detector in a stop line, just in front of the traffic signal. Then this detector mainly observes the stopping vehicle during the red time. So the traffic density estimated by this detector can be very overestimated. So even the same link can appear uncongested state and congested state. So the detector information is quite different depending on their location, okay? So yeah, so these are the challenges of the traffic state estimation in a signalized fleet. And another aspect I would like to discuss is the local view and the global view. So what it means is, so the conventionally, so for the motorway monitoring, we observe the section traffic state because the as I mentioned, the motorway section is quite homogeneous. So this section is quite similar to the other section. So even only the local observation can represent the wider area. So the motorway, so the local observation is okay for the motorway. But if we discuss about the signalized network, as I mentioned, the local observation can be totally different, can lead to misunderstanding. So local observation is like this. If we only focus on this detector, we don't know the state of this area. So the local observation can be a kind of blind. Okay, can lead to a blind control without knowing the other state. So for the urban network, so the local observation is not enough. Instead, we need to think of the network-wide traffic monitoring. So this is another point to be discussed for the monitoring of the urban network, not the motorway network. For the link level monitoring, the idea is very simple. So this is, again, typical diagram of the density and flow. And once we can, so let's say we have the motorway like this, and this is a simple motorway without any on-ramp or off-ramp. And for this motorway section, we can draw this kind of density and flow relationship. And once we can come up with this kind of diagram, okay, so this is the operational target. So to maximize the network link traffic flow, we should keep the density at this level. Okay, and once we know this operational target, then we can implement the control strategy, such as the ramp metering. Like we keep the traffic density of this margin section to be this operational target. So this is the idea of the link level monitoring and the control. And in the network level, actually, we can expect the similar idea. So this example is just for one link, one load section. But if we aggregate the flow and density across the whole network, actually, we can get the similar relationship like this one. So x-axis is the area-wide density, and y-axis is the area-wide flow. And this is called Macroscopic Fundamental Diagram. And once we can once we can get this macroscopic fundamental diagram, I mean the Q and K relationship in the network-wide level, then we can identify the free flow state and congestion state and the control target in between the free flow and congestion. And this information will be very useful to apply the network-wide traffic control like perimeter control or inflow or even the congestion charging. But the question is how we can observe the density. As I discussed, the estimation of the density in a signalized network is quite challenging. So the question is how we can estimate MFD or how we can estimate the variable of flow and density from the signalized urban street. So that's the question. And yeah, from now, I will show you one of the traffic density estimation method for the signalized arterial network. And the idea is actually, the method I will present in this lecture is quite simple and based on the classical traffic engineering knowledge. So I hope you can easily follow the idea. And the idea is so we have fixed detector data and the probe travel time data in a signalized arterial. So these two fixed detector data and probe travel time data is, I think, in most of the cities, we can expect these two types of data. And also we have the conservation principle from the basic traffic engineering knowledge. And by fusing these data and the traffic engineering knowledge, we can estimate the link density from the signalized arterial. And yeah, I will explain this idea. And to introduce my method, I would like to introduce this very classical cumulative plot estimation. So let's say we have two detectors in a road, the detector A in the upstream and detector B in the downstream. And if this vehicle passes through this section, then detector A, so this is a pass, so x-axis is the time, so detector A is upstream. So this is a count at the detector A, and this is a count in the detector B. So this is for the first vehicle. And the second vehicle passes through, then the second vehicle is also counted. So this is a second vehicle at detector A and detector B. And this count is accumulated over time. So this is third vehicle, okay? And this is fourth, this is fifth, seventh. And if we keep doing this, finally we can come up with this, these two curves. So this is the cumulative number of vehicle in the detector A. This is for detector A, and this curve is for the cumulative number of vehicle counted in the detector B. So these are called cumulative plots or cumulative curves. And this simple curve is very informative. Firstly, this horizontal gap between upstream and downstream curve is exactly the travel time between these two locations. Okay, so x-axis horizontal gap is the travel time, and if we look at this vertical gap, then okay, this is a cumulative number at the time t. This is a cumulative number of vehicle counted in detector A, upstream detector, and at the time t, same time, this is the number of vehicle counted at the downstream detector, detector B. So the vertical gap represents the number of vehicle between these two detectors. Okay, the vertical distance is the number of vehicle between detector A and detector B. So if we divide this vertical distance by the distance between detector A and detector B, then we can obtain the density. Okay, so density can easily be estimated if we know the cumulative number of vehicle of upstream and downstream. So yeah, it's very easy. However, this estimation has very strong assumption, based on very strong assumption. Firstly, there is no detector error. Okay, detector A and detector B can perfectly count the number of vehicle. This is very strong assumption. And the second one is there shouldn't be no side street. If there is a side street, then some vehicle is observed at detector A, but if it disappears at the side street, then he will never appear in the detector B. So there shouldn't be the mid-link inflow or outflow. And also, no overtaking is allowed to make this estimation possible. Okay, so this strong assumption is actually very problem. And so let's think what will happen if we have the side street and some vehicle disappear in the side street. Then some vehicle is observed in the upstream detector, but this vehicle just turn at the side street and he will never appear in the detector B. Then the cumulative curve will be like this. So at the upstream detector, all the vehicle can be observed, but in the downstream detector, some vehicle already disappeared. So the two curves are, is not consistent anymore. So in ideal case, the height of the two curves should be same, but now they are different. So in this case, the vertical distance actually has no meaning. Okay, so this is a difficulty for the urban street, because in normal urban street, we have mid-link sink and source section. So the cumulative curves drawn from the detector data doesn't have much information. Then what we can do for this? So the loop detector provides the continuous count. Okay, so we can draw the cumulative curve by loop detector data, but it suffers from the cumulative errors or effect of the side street. Okay. But if we have the probe vehicle data, it is sparse, but it can provide us the travel time between these two detectors. And if we fuse this loop detector data and probe vehicle data, we can modify this gap by fusing these two data. And I will show this idea. Okay, so on one hand, we have loop detector, and also we have signal timing. And by using these two data sources, we can draw the upstream cumulative curve and the downstream cumulative curve. And okay, this is the ideal case. In ideal case, the vertical distance represents the number of vehicles or the density. But as we discussed, generally we have the mid-link sink and source point. So the vertical distance doesn't mean anything in this case. Okay. So on the other hand, we have the probe data. And in this study, I assume the Bluetooth probe data. Bluetooth data, so in your smartphone, of course, you have Bluetooth signal. And also, for most of the vehicle, we have onboard navigation unit. And that onboard navigation unit also has the Bluetooth connection in these days. And if we have the Bluetooth scanner in the roadside, it can collect the ID and the timestamp of the Bluetooth passing in front of the scanner. And with this information, we can know the timestamp of upstream section and timestamp of the downstream section of the same Bluetooth ID. That gives the travel time between upstream and downstream. And by fusing this travel time information, we can correct this gap of two curves. And yeah, this is the idea. So we have this useless pair of curves. But if we have the probe sample is like this. So we know the timestamp of upstream and downstream. We have the pair of timestamps of upstream and downstream. And this pair of the timestamps provides the point-to path. Okay? We know when this vehicle is observed in the downstream and also upstream. So the cumulative curve should pass through this point. So this is the idea. So if we have this pair of the timestamp at upstream and downstream, this curve can be modified like this. Then the vertical distance can make sense, like the number of vehicles. So yeah, this idea is quite simple, but applicable to most of the modern cities. And we tested this simple idea in a simulation environment. So in a simulation environment, we have upstream, we have the signals in upstream and downstream, and we have side street. And in this side street, vehicle sink or some vehicle can appear from this side street. And yeah, we developed this simulation environment and tested this idea against the benchmark density value. So this is the result. So this is this is a simple test using the simulation net environment, because in real world it is very challenging to observe the real density. So we have to rely on the simulation. But in this simulation environment, our proposed density estimation was quite working well, as you see. So x-axis is the benchmark, the real value, and y-axis is the estimation value. So the estimation accuracy was quite good. And also, we conducted the sensitivity analysis of the Bluetooth penetration rate. So generally, the estimation accuracy increases as the Bluetooth penetration rate increases. And what we want to emphasize is even when the Bluetooth penetration rate is quite small, like only 1%, then even in this case, accuracy is over 80%. So this idea is quite simple, but very robust. And so this is a test in a simulation environment. And in this simulation environment, this method is working okay. We confirmed. And yeah, we did some tests in the environment. So this is the one case study. of the coronation drive in Brisbane, where I and Professor Inhi got the PhD. And in this city, so city of Brisbane is quite unique because it has Bluetooth scanners, many Bluetooth scanners. These yellow, you can see the yellow dots. These yellow dots are the Bluetooth scanner. And in this city, they installed the Bluetooth scanner for most of the signalized intersection. And we tested our method for this section. And this is the result of the density estimation for the coronation drive. And unfortunately, as I mentioned, it is very difficult to get the real density value from real world environment. So we cannot compare with the benchmark, but this is the density estimation result. And instead of comparing with benchmark density, we compared it with the travel time of the same section. So at least we can confirm that the peak of the density corresponds to the peak of the travel time. So the estimation result is quite reasonable. Okay, so this is how we estimated the density from signalized arterial. And that test was only conducted in single road section, but we expanded this method to the whole Brisbane network. And yeah, there are many Bluetooth scanners in this Brisbane network. And all the yellow dots are the Bluetooth scanner. And we applied that method to all the sections. There are about 300 sections we can define. So one section is the consecutive link of the Bluetooth scanner, and there are over 300 sections in this network, and we estimated the density for all 300 sections and aggregated it to monitor the network level traffic states. And this is our result. So we estimated the density and flow for all the 300 sections and aggregated it in a network-wide. And we did this for 5 days different data. And x-axis is area average density, and y-axis is area average flow. And you can see different plots. There are 5 types of different plots, and each color represents different days. And even if we plot 5 different days, most of the data is plotted along the same line. Okay, so that means this is called well-defined plot. So 5 different days data are plotted on the same line. So that means this line, this curve, represents the unique network state of this Brisbane network. So once we can come up with this kind of plot, this will be useful to monitor the network-wide traffic state and can be used for the traffic control for the network-wide. And this diagram is for whole Brisbane network. And we also divided the network depending on the network structure and the river. There's a river here in between in the city. And we divided the network considering the network structure and the river. And we also estimated the macroscopic fundamental diagram for each region. And this is the result. And for each region, similarly, we can see the quite well-defined plots for each region. And when we look at region 1 and region 2, the curve is mostly straight. There's no peak. It's just straight. So that means region 1 and region 2, region 4. Region 4 is in a free flow state mostly. On the other hand, if we look at region 2, we have this peak. We can see this peak. So that means region 2 is sometimes it is heavily congested, and so it is a critical state, critical region. And if the network density go beyond this level, the region 2 is severely congested. And I think it is a little hard to see, but when we look at the region 3, so although most of the plots are along the same line, but if we look at the region 3, some of the plot is a little different from the others. And this is actually observed on the 23rd October, and we looked at what happened in region 3 in this day. Then we found out that on 23rd of October in region 3, there is a serious traffic accident. A big trailer crashed into the roadside house, and because of this, the main road in region 3 has totally closed. And this plot is the travel time observed in this area. So the crash occurred here, and this travel time is southbound, and this travel time is northbound. And so during this period in region 3, we observed extremely long travel time due to the severe accident. And this is again the MFD of the region 3. And we compared, so for most of the day, the plot is along this line. But on this day, during this time, the plot is like this, is different from the other days. And we compared this movement of the plot with the police record. And according to the police record, at 8:30, small delay was observed due to the morning peak. So this is a normal delay. But at 7:10, the crash happened and the delay due to the morning peak was observed. So we observed this statement in the police record. And at 8:20, the queue reaches further upstream. And at 8:50, the road reopened and traffic is back to normal. So, and at this time, at 8:50, the MFD also back to the normal area. So the observation from this plot corresponds to the observation by the police officers. So we confirmed that this diagram can capture the network state even in abnormal conditions. Okay, so this is a summary of the MFD. And yeah, let me skip this one. So, okay, let me close my first lecture. So in this lecture, I firstly talked about observation. So we have loop detector and Bluetooth record. So, but these are just observation, and observation is just the partial aspect of the traffic state. So this is just observation, okay? But by effectively fusing these two informations, we can estimate the flow and density, which is the traffic state. So observation and traffic states are totally different ones. And once we can estimate the once we can estimate the reasonable flow and density at the reasonable accuracy, we can, by combining these two variables, we can get a sort of intelligence, like the network performance or regional anomaly analysis or the accident impact. So these are the intelligence obtained from the estimation. So yeah, in this lecture, I wanted to tell this flow. So we have observation, but this is just partial. To make it useful, we have to properly estimate the state and to get the intelligence for the network state and control. Okay. And nowadays, of course, we have more data and very advanced technologies. So the data is can be from connected vehicle, or we even have higher resolution, very good trajectory data nowadays, or the LiDAR data can be another good data source. And also for the technology, methodology side, in this presentation, I presented you to use a very simple sensor fusion one based on the classical traffic engineering knowledge. But of course, we have more advanced technology, advanced methods based on the deep learning method. But even if we have the richer data or the advanced estimation method, the fundamental question is always the same. What we can directly observe, what is observation, and what must be estimated for the good control, and what is the physical constraint to be maintained. So the fundamental questions for the traffic state estimation is always the same. So I'd like you to keep these in mind, even when you use rich data or advanced methods. Okay, so that's all for my first lecture. Thank you very much for your attention.